Alright, so in this video we're going to look at an example that we haven't really seen before. So we have the inverse Laplace of 4s plus 10 over s squared plus 6s plus 34. And we might immediately jump to wanting to use partial fraction expansion, which might work. But what we're going to look at doing here is we're going to try to write this function in a different way using a technique called completing the square. So basically the goal of this problem is to rewrite it with what we're going to call a shift. So you may have heard something like t shifting or s shifting, and that's the goal here, right? If you notice this, none of the s terms have what we'll refer to as a shift. So we don't have like a s minus 3 or s plus 3 or s plus 5 or s plus a, where a is any number. So that's our goal in this case. So we're gonna try to rewrite this problem with a shift here. All right. So the way we do that is actually by something called completing the square. And the way completing the square works is we're going to take this second order polynomial and we're going to try to write the second order polynomial in this way, where we're going to have s plus 3 squared plus 25. And if we notice, we can see that at the end of the day that s plus 3 squared plus 25 is s squared plus 6s plus 34. Now, how do we do that? Well, when we're trying to use completing the square as an approach to the problem, we can kind of use this formula here, where we have something like s squared plus bs plus c. This has to be s squared by itself. It can't be like 3s or anything. Otherwise, we may have to use a more complicated formula for completing the square. But in general, for a quadratic in this form, s squared plus bs plus c, which is what we have s squared plus 6s plus 34, where our b would be 6 and our c would be 34. We can rewrite it as s plus b over 2 squared, which we've done because we have b is 6, so that's s plus 6 over 2 squared, that's s plus 3 squared. And then we have c minus b over 2 squared for c, for this other term. This is 30. Remember, c is 34, so it's 34 over 6 over 2 squared. That's 34 minus 9. That's 25. So that's how we end up with s plus 3 squared plus 25. And that's called completing the square. When we've successfully done something like this, where we, s plus something squared plus some constant out here. All right, so what have we really accomplished in this case? Well, we're not actually completely done. We said that we want to get shifts, right? We're looking for, we write here, looking for s plus 3 as a shift. So notice on the numerator, we still have an s hanging out by itself. It's just 4s plus 10. And notice that even though it's 4s plus 10, it's not a shift. It needs to be s plus, something as an individual term. It can't just be like, 4s plus 10 or 4s, it has to be its own term, the s. So basically, we have the s plus 3 squared plus 25 here on the denominator. And on the numerator, the goal is to match the shift in this case. So the shift here is s plus 3. We want to see if we can have s plus 3 up here, right? And in fact, we've already written it out here, that it's 4 times s plus 3 minus 2. And that's in fact equal to 4s plus 10. If we work everything out, we get 4s plus 12 minus 2. that ends up being 10. But what we've accomplished is we've matched the shift up here on the numerator and matched the shift down here. So that will help us in applying one of the theorems that we'll see in a moment. But I will say that we should definitely break apart both of these functions here, these terms here. So we should have like 4 times s plus 3 over this term here, the denominator, minus 2 over this term here. And that will help us get ready for the next step. So we've basically separated out the two fractions from that bigger one. So in step 4, basically we're looking at what we got with step 3. Now, what can we do in this case? We're going to consider looking at one of the theorems, right? Notice in the first translation theorem, form 2, we're asked with finding the inverse Laplace transform. So we'd be looking at this form of the translation, one of the translation theorems. And I look at form 2, or the first translation theorem, but form 2. Notice how we have big F of s minus a. That means that we're really considering some function, some s-domain function that has a shift, this common shift, s minus a. In fact, imagine if we eliminated the shifts from both of the terms that we have. So instead of 4 times s plus 3 over s plus 3 squared plus 25 and 2 over s plus 3 squared plus 25, we just get rid of those. Every shift we see, every shifted s, we just replace it with an s. So we have an s here, in that first term. We get an s here in that second term. That's just one shift there. Now, this is actually big F of s, because big F of s minus plus 3 is in fact this. So by eliminating the shift, we actually get big F of s by itself. And because the formula tells us that, form 2 tells us that the inverse Laplace of big F of s minus a is e raised to the negative at times f of t, we need f of t. And we can find f of t because we have at big F of s. And the inverse Laplace transform of big F of s is in fact f of t, which is what we need. So using, here we reiterate that a is equal to 3, and we'll need that in the translation theorem as well. But notice the focus here is we're going to take the inverse Laplace of this huge thing here, right? We're going to pull out the constant, so 4 times the inverse Laplace of s plus 3 over s plus 3 squared plus 25 minus 2 times inverse Laplace of 1 over s plus 3 squared plus 25. And so we're going to end up with, we're going to have 4 times the inverse Laplace of this term, and that turns out to be a cosine of 5t, right? We're looking at the unshifted version of this term here. So everywhere we see an s plus 3, get rid of that and replace it with an s and take the inverse Laplace of that. So we get cosine of 5t. And then times the e raised to the negative 3t, because the condition of the first translation theorem form 2 was that we have e raised to the negative at, and a was 3. So there's that term here, and then the 4 is just multiplied in. And it's the same process for the second term. We end up with, this is the one with the shift, right? The form with the shift. Get rid of the shift, so we just have 1 over s squared plus 25. We find the inverse Laplace of that. That's sine of 5t. We have e raised to the at, and we end up with e raised to the negative 3t here. And we just multiply 2 over 5. That was a constant that we had factored out. All right. And in step 6, we have, we're just going to take the inverse. We have the inverse Laplace of 4s plus 10 over s squared plus 6 s plus 34. That was the original problem, and we just combined the results of steps 5. And we factor out the e raised to the negative 3 because that's a common factor. All right.